Welcome to Yaka Digital Network. Today, we're exploring the chemistry that builds and breaks our world. Watch how the heavy rain strikes this exposed iron gate in Kampala. After months of tropical heat and moisture, that strong metal begins to develop a familiar reddish-brown crust. To understand why this decay actually happens, we have to look past the surface layer. Pieces of the iron are literally being stolen away in an invisible, microscopic robbery. We can trace this destruction and our ability to stop it, or even harness it for power, directly to a chemical engine called a redox reaction. It is a process driven entirely by the invisible exchange of electrons. Down at the atomic level, a redox reaction operates as a strict financial transaction. Electrons must move directly from one substance to another. Take a look at this schematic. We use the memory hook oil rig to track the transaction. When atom A gives up an electron, we call that oxidation, because oxidation is loss. When atom B catches that electron, it undergoes reduction, because reduction is gain. Notice how these two atoms form a single unit, known as a redox couple. You cannot have a loser of electrons without a gainer to catch them. The transaction has to happen simultaneously. So if magnesium loses its electrons to oxygen in a chemical reaction, who is the thief and who is the victim? The atom stealing the electrons, in this case oxygen, is the oxidizing agent. The atom donating its electrons, magnesium, is the reducing agent. The oxidizing agent accepts the electrons, while the reducing agent donates them. Engineers rely on this specific, slightly counterintuitive terminology to calculate exactly which building materials will stand strong against the elements and which will crumble into dust. This 3D render recreates a classic laboratory investigation designed to find out exactly what conditions are required to steal electrons from iron. We have three identical nails, one in tap water and air, one in boiled water sealed under an oil layer to block the air, and one sealed in dry air with calcium chloride to absorb all moisture. The results show us that iron will only rust when both oxygen and water are present in the environment simultaneously. Painting the metal creates a temporary physical barrier against those elements. But for long-term survival, industries rely on a more permanent method for the corrugated roofs used across Uganda: galvanization. This cross-section shows exactly how galvanization works. The vulnerable iron core is encased entirely in a protective layer of a more reactive metal, like zinc. Zinc acts as a powerful reducing agent. Through a process called sacrificial protection, the zinc willingly sacrifices its own electrons to the surrounding water and oxygen. Because the zinc pays the electron debt, the iron core remains completely intact. To protect massive infrastructure, we do not simply build thicker walls. We manipulate the strict rules of chemistry by offering the climate a more willing victim. But what if we stop trying to prevent this electron theft entirely and instead force the thieves and victims to work for us? In this dry cell battery schematic, the exact same redox principles apply, but the oxidizing and reducing agents are trapped in separate chambers. Being separated, electrons must travel through an external wire to get from donor to acceptor. That flow of electrons is electricity. We force electrons through chemical solutions in the exact same way to perform electroplating, driving metal ions to coat cheaper materials to make them beautiful and hard. For exams, remember, use oil rig to track electrons. Agents undergo the opposite process of their name, and rusting absolutely requires both oxygen and water. Redox reactions dictate the decay of our physical infrastructure and generate the power running through our digital devices. They are the invisible engines of the modern world. For more comprehensive chemistry lessons and interactive exams, visit us at Yaka Digital Network.